Hello everyone, we have been discussing the summary of different Moore Coulomb failure envelopes extended for unsaturated soils. As we have seen for the Bishop's approach, the effective stress principle becomes sigma dash is equals to sigma minus UA plus xi times UA minus UW. So, this xi f is a effective stress parameter. This provides the contribution of matrix suction to the shear strength of the soil. So, therefore, here as the xi f parameter becomes 1, then this turns out to be Terzaghis effective stress principle. If xi f is equals to 0 and at reference state or at gauge pressure, sigma dash is equal to sigma. So, this is nothing but Coulomb's principle, Coulomb's equation. So, the total stress is equals to effective stress. So, as Bishop has identified two stress state variables such as sigma minus UA and UA minus UW, several tests were conducted by controlling the suction, intraaxial and direct shear operators. So, therefore, several data were obtained in direct shear, where you get the stress ratios tau divided by sigma minus UA and gamma. So, this the stress ratio gets increased with increase in the suction. So, this is for suction equals to 0, that is for saturated state, and as the suction increases the stress ratio gets increased. So, this is how it increases. Even as the soil is normally consolidated or the soil is loosely compacted, as the suction value increases, interestingly at very high suction values it exhibits a peak behavior such as over consolidated clays or densely compacted soils. So, this is at very high suction value, maybe a large suction value. So, therefore, if you plot tau f versus sigma, what we get is the failure envelopes with different intercepts. This is for suction S equals to 0 and this is for higher suction and this is much higher suction. So, as the profiles go up, the angle of the intercept value keeps on changing, increasing. However, the angle of internal friction value nearly same, except that the whatever the small difference we find in the angle of internal friction due to experimental errors, apart from that the angle of internal friction remains same. So, therefore, this expression could be the tau f equals to sigma minus UA, that is net normal stress, plus sigma dash tan phi C plus C dash plus. So, the effective stress is this. So, this is sigma minus UA plus xi f UA minus UW times tan phi dash. So, if this expression tau f versus sigma minus UA is plotted, so this could be written as some C1 dash plus sigma minus UA f tan phi dash. So, this C1 dash is equals to C dash plus xi f UA minus UW tan phi dash. So, therefore, when tau f and sigma minus UA, these two are plotted here, the angle of internal friction remains same phi, but C1 dash varies as UA minus UW changes. So, as UA minus UW varies, the C1 dash becomes C2 dash. So, C1 dash becomes C2 dash and it keeps on increasing as UA minus UW increases. So, this is what is observed. So, therefore, this expression could be used to understand or to analyze the test data we obtained from suction control tests. So, then we have utilized this particular expression to determine the XIF from the measured test data. So, using this expression for direct shear test data, for direct shear, and for triaxial, the XIF is determined from this expression. So, this is the expression for triaxial test. So, in direct shear test, we require C dash and phi dash to be determined, as C dash and phi dash are the strength parameters of the soil at saturated state, and phi dash anyways remains same for even unsaturated soils. Phi dash does not change. So, we conduct two tests, two at saturated state, so that we can determine C dash and phi dash. When we vary UM minus UW, then we get XIF. So, that XIF variation with respect to UM minus UW can be obtained. If the test is on sands, as at saturated state the cohesion intercept is 0, one test can be conducted at saturated state, so that we can obtain the angle of internal friction value, and then we can obtain the functional form of XIF. In triaxial tests also, when we conduct two tests at saturated state, we can obtain C dash and phi dash. Then once these two are known, the principal stress at failure can be determined by varying the UM minus UW. As it is a suction control test, we can control the UM minus UW, and we can obtain the XIF variation with respect to UM minus UW. Once the XIF is known, the functional form is known for us. So, the effective stress is known for that particular soil, and entire stress state of the soil can be determined in unsaturation. So, this is the approach given by Bishop, and several modifications were suggested by Friedland, Morgenstern, and Friedland et al. Essentially, Friedland has conducted several null type tests, where he has controlled UA, the air pressure, water pressure, and the all round pressure independently, and then he increased these values independently, such that when the variation in sigma minus UA and delta sigma minus UW, delta UA minus UW, so these values he started varying independently. So, then he checked the variation in any of these two stress variables are kept constant, the variation in any of these two stress state variables is kept constant, and then he observed that the volume changes are 0. So, that means he has kept these two parameters 1 and 2, the variation in 1 and 2 are kept constant, and other thing can be varied, then the volume remains same. Similarly, the 2 and 3 variation in the 2 and 3 parameters are second and third stress state parameters are kept constant. So, then similarly the volume is constant. Similarly, even 1 2, 1 3 and different combination of these stress state variables, when they are maintained constant, the variations, so the volume does not change. That means any of these two stress state parameters qualify for independently defining the stress state of the soil. So, therefore, he validates the Bishop's approach and confirms that the sigma minus UA and UM minus UW, these two stress state variables can be independently used for defining the soil state in unsaturation. So, further he proposes a new shear strength equation, new failure criterion, where tau f is written as C dash plus sigma minus UA f tan phi dash plus UA minus UW times tan phi b. So, this particular expression is very advantageous to represent the failure envelope clearly when it is plotted in 3 dimensions, tau f in 3 dimension, tau f sigma minus UA and UA minus UW are plotted. So, then the failure envelope can be clearly seen. So, this is how the failure envelope is obtained. So, this angle with respect to UA minus UW is phi b, and with respect to sigma minus UA is phi dash, this is again phi b, and this is the failure envelope. So, the equation defines this particular failure envelope. Initially it was thought that the phi b is constant. So, therefore, we do not require a huge data sets for determining the variation of xi f with UA minus UW. When phi b is constant, only one set of data in saturated state and another set of data in unsaturated states are required, so that using one set of data in saturated state we can determine sigma and C dash and phi dash, and in unsaturated state we can determine phi b when UA minus UW is varied. So, this is what initially thought, and then this was considered to be a simplified and this is more advantageous, but later on it was realized that phi b is not constant. Phi b itself is a function of UA minus UW, and as this was plotted, tau f was plotted with respect to UA minus UW, it was observed that initially this is nearly equals to phi dash when near saturation region of SWCC, and later on it started decreasing and becomes 0 and even becomes negative. So, here phi dash is phi b, sorry, this is phi b, and this phi b is 0 and phi b even becomes negative for some soils. This was observed experimentally. So, therefore, as phi b itself is not constant and which varies with UA minus UW or amount of water that is present in the soils, so we do not draw any additional advantage. This is just similar to the Bishop's approach, except that a new variable is given here. So, this is similar to when you compare this expression and Bishop's expression. So, here the tan phi b is equals to xi f tan phi dash. As xi f is not not constant, so therefore phi b is not constant. So, therefore, phi b anyways whatever we are obtaining phi b from either considering several set of data at different matrix suction values to determine phi b, this approach will be similar to obtaining xi f using several set of data from suction control direct shear and suction control triaxial tests. Later on, Liu and Lykos in 2006 have come up with suction stress characteristic curve called SSCC. So, in the suction stress characteristic curve, they define suction stress as a stress which takes care of all the chemical potential that has decreased due to presence of electrostatic potentials, capillary suction force, capillary forces due to surface tension, and van der Waals attraction forces between the particles, and all our cementation, all any other forces that can come into soils in unsaturation and even at saturated state. So therefore, they introduce suction stress. In the suction stress approach, they have in the expression, that is sigma dash is written as sigma minus UA minus sigma S. So this is suction stress. So suction stress should absorb all different components of all different types of physicochemical capillary force effects in this particular parameter. But later on this equation got diluted by introducing in Liu et al. 2010. This expression in Liu and et al. 2010 later on, this expression got reduced to simply minus SC times UA minus UW, which was similar to Bishop's approach. So if you write, they have substituted sigma S as minus SC times UA minus UW. So this is simply SC times UA minus UW. So this SC is a degree of saturation, but this is a normalized degree of saturation. Degree of saturation itself got now normalized. SC is equals to S degree of saturation at any given point minus residual degree of saturation at residual point divided by 1 minus SR. If SR equals to S equals to SR, this becomes 0. If S becomes 1, so then this whole thing becomes 1. So SC varies from 0 to 1. So then they have substituted, they expressed SC or UA minus UW in terms of they expressed S in terms of UA minus UW, or they express UA minus UW in terms of SC using interrelationship proposed by Van Jenisten equation. So as Van Jenisten in 1980, he has given expression for volumetric water content, normalized volumetric water content, that is 1 by 1 plus alpha times, he essentially says H power n whole power m, and later on he related m and n, and m is related to n by this particular formula for simplification, so that you have only 2 parameters to estimate. So similar expression is used by Liu et al. In 2010. They have used this particular form, and they have used alpha and UA minus UW power n power 1 minus 1 by n. So this expression they used. Then the effective stress equation is written as in terms of SC. This can be written as SC power n by 1 minus n minus 1 whole power 1 by n, or in terms of UA minus UW, this becomes one plus whole power n minus 1 by n. So these two expressions were given, and again the estimation of this is a continuous form. So if you have the data of SWCC, then you can fit to this particular expression, Van Jenisten expression, and you can obtain alpha and n parameters. So if you know the alpha and n parameters, you can obtain the suction stress characteristic curve by plotting sigma s versus UA minus UW. If you do not have this data, again using the same expressions similar to Bishop's, so the sigma s can be written as minus tau f minus c dash minus sigma minus UA f tan phi dash tan phi dash. This is for direct shear, and for triaxial, so this becomes sigma minus UA, sigma 1 minus UA at f minus sigma 3 minus UA f tan square 45 plus phi dash by 2 minus 2z dash tan 45 plus phi dash by 2 by 2 tan 45 plus phi dash by 2 tan phi dash. So, here similar to Bishop, the C dash and phi dash can be determined if the tests are conducted at saturated state, and then beyond that, after that, when the direct shear test is conducted at particular UM minus UW, then sigma s can be determined at different UM minus UWs, and sigma s and UM minus UW can be plotted to obtain the suction stress characteristic curve SSCC. Similarly, this is with triaxial test. Triaxial shear test data is analyzed in this particular manner. So, essentially all these approaches are similar to Bishop's approach, where either to determine Xi(f), if Xi(f) is known, the tan phi b, the phi b parameter in Fredland and Morgenstern can be obtained, and the suction stress characteristic can also be derived if Xi(f) is known. So, therefore, essentially all these approaches are same, and still, so to determine the effective stress of unsaturated soil, we require Xi(f) or phi b or sigma s. So, therefore, we can determine effective stress, and we can understand the failure envelopes in unsaturated soils. Let us discuss a new topic, that is volume change in unsaturated soils. In our basic soil mechanics, we study the volume change behavior of soils in consolidation. So, when the load is applied on saturated soil mass, either isotropically applied load or under K0 condition, isotropic load is applied in triaxial tests on saturated soils, and under K0 condition this is conducted in odometers. When this loading is applied, the excess pore water pressure that is generated in the soil mass, soil pore system, will get dissipated through the boundaries, and once this got dissipated, the volume changes, because there are only two phases, that is water and soil solids. As water goes out, the volume of the sample decreases. So, this decrease in volume is called consolidation, and the volume changes are very important in the field problems, especially when you have expansive soils located, and when you are constructing a building or when you are constructing an embankment, the consolidation settlements are very important. Often we theoretically determine the coefficient of consolidation in the laboratory by collecting the sample from the field and conducting odometer tests under field conditions, and the coefficient of consolidation is obtained, and this coefficient of consolidation is utilized in the field for obtaining the rate of consolidation settlement. Similarly, to estimate the consolidation settlements, we load the sample and let it consolidate, and again we increase the load and let it consolidate. Similarly, we obtain an E log P curve, that is E versus sigma dash, effective stress equation, effective stress relationship. This constitutive relationship is similar to stress strain relationship. From this you get bulk modulus, that is MV or 1 over MV, and you get hydraulic conductivities at any given point, and similarly using the entire constitutive relationship you will obtain coefficient of compression Cc. So, from this we can obtain the consolidation settlement, or using the bulk modulus, that is 1 over MV, we can estimate the settlements. Often this Terzaghi's one dimensional approach is criticized, and for highly expansive soils, or when the soil is highly plastic, or when it is slurry state like mine tailings etc., a large strain consolidation approach is used, because Terzaghi's consolidation approach uses small strain approximation. So, large strain consolidation approaches are also available. So, however, all these considerations are based on soil state to be at saturated, completely saturated. However, when the soil is unsaturated, then the change in the volume, how to determine the change in the volume, how to analyze the change in volume. So, we have often seen that when initially a saturated or slurry state soil is kept in a small container. This is a slurry sample, and when this is exposed to the environment, so slowly the evaporation takes place. Due to this evaporation from the soil mass, so the water content of the soil decreases. So soil enters into unsaturated state. So this is often seen as the volume of the sample and water content are plotted. So initially the sample state is somewhere here, sample water content is at maybe slurry state or at liquid limit state. So this is done in shrinkage tests, shrinkage limit tests. So this is the initial state where it has particular volume and particular water content. So when the soil is subjected to drying, because when the soil is kept in atmospheric conditions, so due to the RH and temperatures, there is some suction load that is applied on the soil mass. So because of which soil volume decreases up to certain water content, and beyond that this is non-linear, and the change in the volume ceases to be exist at one particular water content, which is called shrinkage limit. So up to one particular water content this is linear, so the volume decreases linearly with water content. So this also can be plotted as degree of saturation, void ratio. So because the volume of the soil is known and water content at any given point are known, so we can obtain what is the total mass is also known. Mass of the soil sample is known, because when the water content measurement is taken, the soil is weighed, right. So therefore the density of the soil, bulk density of the soil is known, because total mass and total volume is known. So knowing the bulk density, the dry density of the soil can be obtained using this particular expression. Knowing the water content, the dry density can be obtained. Knowing the dry density, knowing the specific gravity, we can obtain the void ratio. So that is how the void ratio can be obtained, and which is plotted on y-axis, and on x-axis instead of W, if we plot with WGS, we see that there is a 1:1 line. There is a 1:1 line exists up to certain water content. That means the degree of saturation of the soil remains same, and beyond that degree of saturation becomes less than, here degree of saturation is 1 and here degree of saturation is less than 1 beyond this, and here degree of saturation may remain same constant, because the decrease in water content is nearly constant, and it almost ceases to, degree of saturation slowly becomes close to approaches to 0. So the volume of, see here it approaches 1:1, so therefore if E is equals to Wg by SR, and as SR equals to 1 up to here, this follows 1:1 line. So SR is equals to 1, so Wg and Wg, so therefore it plots 1:1 line. So as the soil is subjected to drying, the degree of saturation remains same up to one particular water content, and beyond that the degree of saturation decreases, and volume of the sample continuously decreases from the beginning itself. And what happens to the suction? Suction of the soil increases. Here the suction may be 0, the suction either psi or S small s is equals to 0, the suction is very high, suction becomes very high, maybe in terms of MPa you may be able to measure it, depending on type of soil also. So this particular thing happens in expansive soil, or soils which exhibit volume change during drying and wetting. So this is a drying process. So soil exhibits a volume decrease during this particular process. Similarly, when the soil is subjected to wetting, the soil volume starts increasing. So, how much it increases or how the suction varies? Here the suction volume, the degree of saturation, the volume, so which can be represented with void ratio, and suction. 3 different parameters are changing. When the suction is increased, the volume may be decreasing and the degree of saturation may be decreasing. So, similarly these 3 parameters are dependent on one on each other. So, to understand the soil behavior, we need to conduct the tests under controlled environment by controlling suction, and how these parameters are changing, this is what needs to be done. Similarly, this particular tests are conducted when there is no external load, but similar tests may also exist when we are constructing a building or any other structure on soils. So, this may be foundation, and you may have a groundwater table located somewhere else here. So, this is a groundwater table and this ground surface, and you may have a fully saturated region, that is a capillary region, maybe up to here. So, this is equal to the air entry head height or capillary height. So, beyond that this is unsaturation. So, if you see the profile, so if you see the variation, so the water content varies in this particular manner. Water content nearly same or degree of saturation is same, but beyond that it decreases in this manner. So, when the water content decreases in this particular manner, so this is maybe degree of saturation and this is height. So, the degree of saturation may decrease in this manner. So, essentially when you are constructing some particular building in unsaturated region, this is unsaturated region, and this is saturated region, and this is saturated region. But here the suction component exists, suction is more than 0, here suction is 0 or suction is less than 0. So, that means there may be a positive pore water pressures exist below the groundwater table, but here you will have suction value more than 0, and here the suction value will be very high. So, when you are constructing such building or when you are exerting some loading due to construction activity, how the soil volume changes is an important question that need to be addressed. For that, some suction control consolidation tests are also conducted. Suction control odometer tests are conducted. In the suction control odometer tests, we have odometer similar to what we have seen earlier. You have 2 porous plates located on top and bottom of the soil sample. And this is your soil sample. And here there is a ring which keeps the soil sample intact. There is a ring. And this is a loading plate. and load is applied on this, and there is a pipe or connector to circulate the PEG solution. So, this is osmotically controlled odometer. So, these are connected. This is the PEG solution which is circulated into the around the soil sample boundaries, so that the PEG solution comes in contact with the pore water of the soil. There is a semi permeable membrane which is kept here and again here. So, due to this semi permeable membrane, the PEG molecules are not allowed to enter into the soil sample. So, therefore, as the PEG solution concentration is high on the at the boundaries, so the water will leave from the soil and the water content of the soil decreases. So, when the PEG solution concentration, which provides a suction value of say 100 kilopascal, due to this 100 kilopascal suction that is exerted on the soil, so the water content decreases. Due to decrease in the water content, so under either the applied load or even without the load, the soil volume will decrease. So, similarly, this is osmotically controlled test. And similarly, using the access translation technique. So, where at the top and bottom of the clay sample or soil sample, you will have higher entry disc here, HAE disc, and you will have low air entry disc located at the top. That means coarse porous stone is located at the top and higher entry disc is located at the bottom. So, this is connected to a gas chamber. So, the air pressure can be applied and through which the water pressure can be applied, and this higher entry disc is always kept saturated. So, this it maintains a very good hydraulic contact with the soil pore water. So, then the pore water pressure is maintained through this chamber and from the bottom, and air pressure is maintained from the top. So, this way given UA minus UW is maintained within the soil sample, and so the volume of the soil sample can be obtained by connecting to by measuring the height of the soil sample using dial gauge. So, here also you will have a dial gauge which is located and which measures the change in the volume. You will have a dial gauge, so which measures the change in the volume of the soil sample. So, this way void ratio can be measured, suction can be controlled, and the water content of the soil can be obtained by having independently established soil water characteristic curve. Therefore, knowing the suction, the water content, or knowing the suction, either water content or degree of saturation can be obtained. So, this way the independently or these three parameters can be obtained from these particular tests, and the constitutive relationships can be developed for different soils. Similarly, this is at a K0 condition, because when you apply a load, soil exerts pressure on the boundaries. So, this is K naught condition, but in triaxial similar test can be conducted where we isotropically, so this is the soil sample where we isotropically consolidate. So, we exert an all round pressure of sigma 3 on the soil sample. So, therefore, soil can be isotropically consolidated. So, this is isotropic consolidation. So, therefore, in suction controlled triaxial tests, the isotropic consolidation test can be conducted. So, therefore, here the total volume that can also be measured. So, amount of water that is leaving that can be determined. So, therefore, water content or degree of saturation and the void ratio, because change in the volume is also known, and suction which is controlled, all these three parameters can also be obtained in suction controlled triaxial tests. If we look at the different data that we get from these tests, so these are either plotted with void ratio or often this is plotted with specific volume. The specific volume which is nothing but 1 plus E, 1 plus void ratio, because void ratio is volume of voids by volume of solids. So, this is nothing but total volume by volume of solids. As volume of solids anyways is constant, how the total volume changes with by applying different suction or mechanical loading can be obtained. Therefore, specific volume is often used. So, the specific volume versus time for different applied loading, if you see. So, when the suction is 0, so not much change, but as the suction is increased, you would see that the specific volume will decrease with time. So, this is the equilibration time. So, with equilibration time, the specific volume decrease for different suction higher than 100 kilopascal. Similarly, specific volume is plotted with the mean stress under different suction conditions. Mean stress, so that is P net when it is plotted. So, when the soil is completely saturated, so this is what we get. This is typically a E log P curve, similar to E log P curve. This is at S equals to 0, this is at S equal to 0. So, that is purely saturated soil, and for other soils a dry condition, because if the soil is expansive soil, the initial volume of the soil sample may be here. Due to saturation initially under this particular seating load, when you saturated, the volume, total specific volume becomes this, and when you consolidate, this is the curve that exhibits. So, initially, for example, under 100 kilopascal, for initially the sample may be somewhere here, specific volume may be somewhere here. When you saturate it up to 100 kilopascal, so the initial state of the soil may be here. So, this is at S equals to 0, this is at X equals to 100. So, then if I consolidate, so it may consolidate somewhat like this. The slope of the curve change, because there is a suction, because of which it does not consolidate as much as it does not compress, or volume does not change significantly as it happens when the soil is completely saturated. So, as my suction is increasing, I obtain different profiles. So, here the initial state of the soil sample is different because my suctions are different. Here this is much higher than 100 kilopascal, right. So, initially when the soil sample which is taken at dry state, probably it has a suction of maybe 1000 kilopascal. So, then the specific volume may be somewhat here. When I reduce the suction within the soil into 100 kilopascal, then that means some wetting takes place, because of which the specific volume becomes this much. Then I consolidate. Similarly, if I want to consolidate at saturated state, I allow the soil to completely saturate or wet it at seating load, then it comes to say S equals to 0, and then after that I consolidate. So, I get different profiles like this for different loading conditions. This may be at completely dry state. So, such kind of profiles you can obtain. Similarly, the specific volume can be plotted with suction for drying and wetting. So, when the specific volume is, when the suction is increased, the specific volume will decrease, because the specific volume, the increase in the suction, the water content decreases. So, due to decrease in the water content, the specific volume will decrease. So, when you wet it, the specific volume increases, but it does not increase as much as we obtain in drying state. Similarly, when you draw U minus UW, that is suction versus P net, net normal stress. So, during the drying process, the net normal stress on the soil sample increases, which decreases as you wet it. So, this is drying and this is wetting. So, the hysteresis behavior can be studied very well, and while studying the hysteresis behavior, the specific volume changes and the drying and wetting, that hysteresis can also be studied very well in this particular suction controlled odometer tests. Further, the void ratio versus log sigma can be plotted. When you plot this void ratio versus sigma or sigma dash, the effective stress, what we see is the suction value when it is 0. So, this is a typical consolidation test result. When S equals to 0, if you assume that the E versus log P dash relationship is linear, then this is what we obtain. And when the soil is expansive soil, assume that this is the consolidation curve. When the soil is dry, completely dry, so the initial state of the soil may be somewhere here. The void ratio will be less than the void ratio of the saturated soil under the same load. Under this particular load, the soil's void ratio will be smaller than the void ratio that we obtain for the completely saturated soil. So, for under the complete dry state, when you load it, so this is compression, this is not called consolidation. When you compress the soil, so the change in the volume will be negligible. So, which changes in this particular manner, right. So, because this is a dry soil, when you are compressing by applying the loading, so change in the volume or the void ratio is not significant, therefore, this is the curve you get, or this is the relationship you get, and this is at S equals to much greater than 0 or nearly dry state, and this is completely saturated. So, now when the dry soil at any particular loading if you subject to wetting, how does it behave? For example, at this particular loading, if I wet the soil sample, for example, the soil sample is now initially compacted to one particular density, and I will explain this one again. Initially, the soil sample in a dry state, which is taken in compacted and kept in odometer, Now this is under seating pressure, this is a seating pressure. Now this is completely saturated. So when this is completely saturated, this is the void ratio the soil obtains at fully saturated state. Now when we consolidate, this is the curve we get. So this is the consolidation curve. So at each load increment, we wait for soil to consolidate, and after it consolidates, this is the equilibrium void ratio, and again we put next loading, and that's how we consolidate the soil sample. So this is what happens. Now if you take dry soil sample with the same density and which is at this particular state where the void ratio is E, now if the soil is compressed by applying loading, and this is what we obtain, dry state. So now at any given loading, if the soil is subjected to wetting, so what is expected is the soil will swell, or the volume of the soil sample increases, which is called swelling. Similarly, another soil sample is taken, which is again compacted to the same level, and again which is subjected to this particular loading, and again which is allowed to wet, which is wetted, then it exhibits swelling, and then it shows this behavior. And similarly here a small swelling is exhibited. Similarly here, when the soil, this is in this condition, which is wetted, which exhibits a decrease in the volume, which is called collapse. Similarly the soil, when it is here initially, when it is allowed to wet, when it is wetted, it exhibits a collapse. Similarly here also it exhibits a collapse. So even swelling soils are expansive soils. When the soils are subjected to wetting under different confining stress or applied stress, it may swell or collapse, or the volume may increase or the volume may decrease depending on the stress state of the soil. So therefore the swelling and the collapse behavior of soils can be determined or studied very well by conducting several tests. The swelling and collapse behavior of soils can be studied by analyzing their behavior under suction controlled environments. So swelling and collapse behavior we detailedly see in the next class. Thank you.